Welcome to the lecture. In our earlier lecture of this section, we have understood what is vibration, why it is important, how it is measured, and what are the causes of the vibration. In this section, we will try to use the vibration spectrum and waveform to detect the machine failures, and you will discuss various techniques, methods, their advantages and disadvantages, and how they can be used in industry to detect the fault in the machine and give us the prior indication of failure. In other words, how the vibration analysis can be used as a great condition monitoring tool that we are going to discuss. So before starting, what is vibration analysis? Vibration analysis is the process of measuring the vibration level and frequency of a machinery and then using the information for analyzing the healthiness of the machinery or its components. Though the theory behind the vibration analysis can be complicated, there are lots of mathematics, lots of calculation graphs, so which you may find in other courses, and sometimes it overwhelms you. But in practice, all it starts with a simple accelerometer, an equipment running makes some sort of vibration. The accelerometer attached to that equipment picks up that vibration and converts it into a voltage signal that is proportional to that vibration amplitude and frequency, and we measure the amplitude and measure the frequency and get a conclusion about what it is, what going on in the equipment. The amplitude denotes the severity of the vibration and frequency denotes the characteristics of the fault. So how the data is being collected? The data is collected through the accelerometer. So in the accelerometer we get the data in form of very low voltage, maybe in the millivolt level, which cannot be further used. So there are certain signal conditioning circuit that is being used which converts it to volt. That millivolt that is generated is proportional to, or you can say that millivolt that is generated is the function of amplitude and voltage, amplitude and frequency of the vibration, and then it is converted to volt, and there it goes to the data collection software where its data is being stored in the database, and then from the database we can fetch the data to make some sort of data visualization. The data visualization can be in form of the time versus velocity or amplitude versus time, which can be like this, or we can have a spectrum view where the amplitude versus frequency, where we can have a view like this. Further, when these two waveforms we have, then we can start analyzing. Analyzing can be through a trained expert person or it can be through algorithm. it is going at present time. So then we can get the final conclusion or report what we do, and based on this conclusion we can make maintenance plan to do the maintenance on that particular equipment. We can fix the time of overhauling of the machine and so on. Next, what we can get from the vibration analysis? What type of fault can we detect? During our lecture in the causes of the vibration, you can remember that we have identified the multiple causes through which the vibration can occur in the equipment, and all the causes that were listed there can be traced back to the vibration analysis. What I mean to say is, through the vibration analysis you can detect all the faults like imbalance, if there is a bearing failure, if there is a misalignment, if there is a bent shaft, if there is a resonance, mechanical failure, electrical motor failures, gearbox failure, or there is a some issue about driving the machine, there is misdriven, the machine is overdriven. All this can be inferred from the vibration analysis. Now there are certain vibration analysis methodology through which we need to go, and if we go through this methodology we can get to some conclusion. These methodologies are developed by research institutes, developed by various companies, various industry professionals, and they have been found effective. Over time they are used again and again, and people have got expertise in these methodologies, and there are case studies, there are thousands of numericals, thousands of examples that through this type of analysis the problem have been solved. So there are practical examples, where the people got benefited from using different methodologies. So we will discuss some of these methodologies, and we will discuss some common methodologies, some advanced methodologies that are being used in the industry. So we will not go very detailed about each of the methodology, because each methodology can make a completely separate section to be discussed, and that is beyond the scope of this particular course. So we will just touch upon the various analysis techniques, and this will suffice you for the CMRP exam, and also give you a fair amount of knowledge about the vibration analysis best practices also. So after that you can go to the particular industry, and you can check on practice if how it is being done, and you can start implementing it, but your basic foundation can be built through this course. And almost all topics that comes in the CMRP exam are also being covered in this section. So before wasting further time, we can start discussing various methodologies. So first methodology that we have mentioned is already being discussed earlier, that is time domain analysis, where we plot a amplitude versus time plot. We give amplitude versus time plot is made, and this amplitude can be in terms of velocity, it can be in terms of acceleration, or it can be in terms of displacement. So you get this type of curve, and by analyzing the amplitude and analyzing the time it is taken, we can conclude about the type of fault. Frequency domain analysis, there is a better version of the time domain analysis. It can be frequency domain analysis can be used more easily to detect fault, where we plot amplitude versus frequency plot we make, and this is normally also known as the spectrum. Okay, and another is a joint domain, because the vibration signals vary with time, so calculating more than one spectrum at once can be very useful. To do this, a joint time technique called Gabor-Wagner wavelet can be utilized. This technique is used to calculate the variation in the first Fourier transform, including the short Fourier transform. So this is a joint domain technique. Next, we have modal analysis. Modal analysis is takes the measured frequency response function of a piece of machinery and puts them into some sort of computer model. The computer model can be displayed with animation of all different vibration modes. The model can be adjusted by either adding or taking away things like mass or stiffness to see the effects on it. Next is order analysis. Order analysis is the variation of FFT analysis and is mostly used to quantify the variation in the machines with the varying revolution per minute. In other words, uh, order analysis is the frequency analysis where the spectrum frequency axis is shown in orders of RPM rather than Hertz, and the term order refers to the frequency that is multiple of the reference rotational speed. For example, if a vibration signal is equal to or twice the frequency of the motor rotation, the order is 2. Uh, it is basically it is a different name, order analysis, but basically this is frequency domain analysis, or you can say this is basically a spectrum. Only there is a change in the uh, x-axis. How it is, I can show you. This is here also you are plotting the vibration signal in terms of amplitude, and here in we are plot in this axis we get normally frequency. Okay, now frequency is expressed in cycles per second, or you can say in hertz, but instead of directly plotting frequency like 100, 200, 300, we can have an idea about the RPM of the machine. So if say RPM of the machine is 100 cycle per second, so this is 1x. If so, next will be 2x, next will be 3x, 4x, like that. So instead of plotting in terms of directly in terms of frequency, we can plot in terms of the RPM. So this frequency denotes equal to RPM. This is twice RPM. This is thrice RPM. So this plot gives additional information about the speed of the machine. So um, you can plot again your curve here. So you can have a peak here, you can have another peak here, you can have another peak here. So what gives you better idea, because you know, okay, I have getting the twice the speed of the machine, so this can be the fault. We are getting the thrice peak of the machine, so this can be the fault. So more information is given to the curve, and it is far more easy to interpret about the fault. Uh, Now there is a simple example that is being given. Okay, this is a fan that you can see. This is a shaft, and there are one, two, three, four. There are total seven blades to it. There are total seven blades to it, and there are four coils. There are four coils here. Now the shaft is rotating in this fashion. This gives you, sorry, the shaft rotation, and this gives you the blade spectrum. This gives you the blade spectrum, and this gives you the coil spectrum. So when we are getting the vibration, we will get the addition of all these three, and this comes like this. So it is very difficult to interpret, right? So we can do the FFT on it, and we can plot amplitude versus hertz. So here you see they have plotted. Now the RPM is 3300 RPM is equal to 55 CPS. So 55 CPS we are getting one peak. So this is 1x. Now this is 4 times. So this is 4x, we are getting another one. And this is I think 7x. So 7x we are getting another one. So this is 1x. This is of the shaft. This is of the coil, and this is of the blades. Now, now see how we can now interpret the vibration results. Say you can take the vibration reading or this spectrum. Say when you install this fan, maybe on 1st of January 2021. Okay. Now, after 6 months, you can again come to it and take the reading. In that time, suppose one of your signal is getting a higher vibration compared to the earlier one. Okay, so if you have the earlier data also, now you have data, and you can compare the earlier data, or you can simply have some design specification that this is your alarm level. Below this is the safe working. From this to this is your warning port level, and after that it is danger. So you can make the report and hand over to the maintenance group, and they can accordingly take action on it. So hopefully I am able to understand you the what is the why this type of analysis is being used, and why the order analysis is very effective, and it can directly gives you the faults, and anybody can detect that there is some fault into it. So next technique is envelope analysis. In envelope analysis is a form of vibration analysis that can detect the impact with a very low energy, often hidden by other vibration signal. Envelope analysis can be used for diagnostic and investigation of the machinery where the faults have an amplitude modulating effect on the characteristic frequency of the machinery. Examples include faults in gearboxes, turbines, or induction motors. Envelope analysis is also an excellent tool for diagnostics of the local faults like cracks or spalling on the roller element bearing. So every analysis has some merits or some demerits, And these analysis techniques are introduced due to some shortcomings of the earlier methods. Another very important technique is orbit analysis, or we can tell it a relative measurement of vibration. So this is the orbit analysis. Instead of one proximity, now we have two proximities which are at a certain angle. So this is an X vibration probe, and this is a Y vibration probe. And as the machine is rotating, two plots are being generated, and these two plots, this is maybe X, this is Y, and these two can be combined into a single plots, and it looks like a orbit. That's why it is called orbit analysis. In this case, the two probes are separated by 90 degrees. This is usually used to detect the shaft vibration caused by the oil while whirling around inside, causing the journal to move. Now we have discussed different methods. There are different categories of vibration measurements also. For example, spectral analysis. Spectral analysis is, we already told you that this is amplitude versus frequency analysis. And this particular line is very important. We have already discussed it. Where there is a peak in the frequency signal, that is more likely the source of vibration. Spectral analysis is used in rotational speed of shaft and how often tooth meshing occurs on a pair of gear wheels. Okay, so we have already discussed it, no need to discuss it again. Another is discrete frequency monitoring. This is when you need to monitor a specific component within a machine. A discrete frequency monitoring measures the vibration level being generated at a particular frequency, which that component is expected to generate it. For example, if you want to look a certain shaft in a machine, you turn the monitoring to that machine's rotation speed. And discrete frequency analysis is calculated using the FFT algorithm. You can think of the example I have provided during order analysis. We have a plot of amplitude versus frequency, and we are interested only in a particular frequency, that is the rotation speed. Maybe it is 55 Hertz, and here whatever the peak we get, we'll only take that, and we will remove all other signals, and over the time we will analyze this particular peak, whether the amplitude of this particular component is increasing or decreasing, like that. In that example also, you can remember that this peak is representative of the shaft. So if we want to monitor the shaft only, that we can use this kind of discrete frequency monitoring technique. Another is shock pulse monitoring. It is also a predictive maintenance technique that monitors the roller element bearing with a handle instrument. The handle instrument gives off a natural frequency that is excited by the shocks and vibration generated by the rolling bear ring. In other words, When the two pieces of the metal touch each other while in the motion, shock waves are being developed from the impact, which travels through the metal, and this shock wave is used for the shock pulse monitoring. Difference between the shock pulse monitoring and other vibration measurement technique is that shock pulse monitoring, the transducer responds and resonant to the frequency of 36 kHz only, which ensures that a calibrated response and accurate measurement to the shock pulse. So this is also a specialized technique used in certain equipment, critical equipment, where we vibration analysis is not enough and we need further analysis of the issues, then shock pulse monitoring can be used. This is far more accurate and far more reliable than other vibration techniques. Another measurement technique is kurtosis measurement. Kurtosis gives you the measure of the spikeness of a random signal. Signals with the higher kurtosis value have more peaks that are greater than the 3 times of the signal root mean square value. In vibration analysis, kurtosis is used to monitor the fatigue development in roller bearing in the simple instrument. This kurtosis measurement is basically used for the fatigue development in roller bearing. So don't get overwhelmed by these terms or by these curves. Uh, because we need to only know that there is a technique called kurtosis measurement, and kurtosis measurement is mainly used to monitor the fatigue development in the rolling bearing. That's all we need to know for the CMRP exam and also for the basic vibration analysis training. But it gives you an idea that there is a technique named kurtosis measurement. You can further, if if your industry or somewhere, if you can find this, you can correlate with this and you can go for further study into the topic. So I have a full course on the vibration analysis techniques where we discuss all this in greater detail. So for the time being, just remember that kurtosis measurement is a vibration measurement technique which is being used to measure the fatigue development in the rolling bearing. Next is signal averaging. Signal averaging is another uh, technique where we take the measurement, we take the various measurement and then average it. This is particularly important if we go for low frequency measurement because they need a longer averaging time to get a statistically accurate spectrum. Signal averaging is often used in monitoring of a gear in relation to its rotation speed. But signal averaging is very common thing and it is inbuilt within various vibration analyzers. Another technique or method it is Capstrom analysis. Originally, it was invented to characterize the seismic echoes produced by earthquakes and bomb explosion. Capstrom is used to look at the repeated pattern in the spectrum. Repeated pattern in the spectrum are sensed as one or two components in the spectrum with the multiple sets of side bands into it, which can be confusing. The capstone separates those sidebands like the way the spectrum separates repeated time patterns in the waveform. Spectrum analysis is often utilized to look at the interaction between the rotational frequency of the bladed rotors and blade passing frequency. Another example is examining the gear tooth meshing frequencies and gear rotational speeds. So, what are the tools and what are the technologies that we can use? There are multiple different kind of devices. There are portable devices, there are wireless devices. There we are nowadays it is coming with the connectivity with the smartphone, and it can be app based, it can be 3D simulation. It is coming with the preloaded fault database also, so that you take the sample from through the accelerometer, feed it into the analyzer, and the analyzer directly tells you, okay, you are getting this type of curve, is this type of spectrum. So these are the possible reason for this. So you can just cross check it with something else, and then you can confirm, okay, yes, this is the reason of this type of vibration spectrum. So you can reach the conclusion very easily, and the amount of training that is required or amount of skill set that is required is also going to reduce with the advancement of the technology. So the techniques we have discussed till now is it is not continuous vibration monitoring. It is we are monitoring the vibration uh, maybe some once a week, once a month, or once 6 months, depending on the criticality and the type of the machine or type of the fault that we're going to experience. But there are some machines where we need continuous vibration monitoring, because that component is very critical. That component is very critical. It need to run 24/7. It need to run 24/7 to cater the whole complex. And if the fault in that machine can cause havoc, huge amount of money, and your reputation, loss of reputation, all these things can occur. So in that kind of machine, you need continuous vibration monitoring. In continuous vibration monitoring, there are multiple proximity sensors or accelerometer that are installed, yeah, on the gearbox, on the driving end, on the non-driving end, and that data is directly come to the DCS panel or the SCADA system, where you can see the data. And if there are also alarm associated with it, so if the value of a particular vibration probe goes beyond a limit, it will generate an alarm, and accordingly action can be initiated on it. Also, the continuous vibration monitoring is important for machines which are hard to reach, with a very difficult location, like machine which are in the rooftops, which are on the cooling tower. Those operating on the high temperature areas cannot be continuously accessible for the persons. It is uh, it is better that we install the vibration, some sort of vibration monitoring into it.